ֆակուլտետը եւ հետով մտել եմ ասպիրանտուրա, դարել եմ ասպիրանտ բյուրական այս խայտարանում եւ բան երկու հատ Համբարձումյանի բաժնի տեսական աստրոֆիզիկայի բաժնի եւ Արտուր Նիկագասյանին միասին եւ սկսել եմ իմ կյանքը տեսական աստրոֆիզիկայում, պլազմա ֆիզիկսայում եւ հետո ժամանակ որ պերեստրոյկան սկսեց ես ստացել եմ մի քանի հատ հրավիրում գնալ Եվրոպա, մասնակցել կոնֆերանս եւ դա շատ կարեւոր է եղել սկսել շփվել գիտնականների հետ եւ պարզեց այն ժամանակ որ եւ Համբարձումյանը այն ժամանակ շեշտեց որ առանց անգլերեն հնարավոր չի ոչ մեկի հետ շփվել որտեղ գիտությունը դա շատ գլոբալ երևույթն է եւ եթե ուզում ենք ինչ-որ հարցեր լուծենք պետք է լուծենք միասին չկա այդտենց գիտություն որպես ռուսական գիտություն, հայկական գիտություն, ամերիկական գիտություն, ֆրանսիական գիտություն, կա գիտություն եւ պսևդոգիտություն, pseudoscience տենց որ եւ այսօր այս բոլոր գիտական հարցերը այդքան կոմպլեքս են որ շատերը պետք է հարցերը լուծել բանի մեջ, կոլեկտիվի մեջ, թիմի մեջ դրա համար եւ թիմի մեջ տարբեր գիտնականների հետ աշխատելի է տենց որ ես չնասած որ սկզբից աշխատել եմ Եվրոպայում, Սկանդինավիայում, Շվեդիայում, Դանիայում, հետո Ֆրանսիայում եւ Գերմանիայում եւ հասկացել եմ ինչքան փոքր մեր մոլորակն է եւ ինչքան կարեւոր է մարդկանց սկսել աշխատել հետո 94 թվականում ինձ հրավիրել են գալ Los Alamos National Laboratory եւ մեկնել եմ ես 94-ին ես սկսել եմ աշխատել Los Alamos-ում եւ 95-ից ես NASA Goddard Space Flight Center-ում Վաշինգտոնի կողքը այդ լաբում եւ արդեն այդքան տարի աշխատում եմ այստեղ եւ նույն գիտությամբ զբաղվում են բայց իհարկե իմ հարցերը մի քիչ լայնացավ բայց նույնպես իմ խումբը իմ խումբը շատ լայն է աշխատում եմ եւ ֆրանսիական, գերմանական, բելգիական, ճապոնական գիտնականների հետ, որովհետեւ այսօր պետք է մի քիչ պատմեմ դրա մասին, ինչու համար այդ տեսակետի կոլաբորացիան շատ կարևոր է, առանց այդ կոլաբորացիան հնարավոր չի մեծ հարցեր լուծել։ Կարելի է փոքր հարցեր լուծել, բայց պարզվում է, որ փոքր հարցերը չի տալիս մեծ նկարը եւ այսօր որ մենք ունենք մեծ հերադիտակները, մեծ կոսմիկական պրոջեկտները, մենք պետք է հասկանանք ինչ ու պետք է դիտենք։ Տենց որ ես սկսել եմ որպես աստղաֆիզիկոս, հետո դարել եմ արեգակնային ֆիզիկոս, heliophysicist, տենց կոչված heliophysics, գիտնական եւ վերջերս 5-6 տարի առաջ դարել եմ astrobiologist, աստրոբիոլոգիական գիտնական, որտեղ ես կարծել եմ հնարավոր է եղել օգտագործել իմ գիտելիքը աստրոֆիզիկայի, արեգակնային ֆիզիկայի, քիմիայի եւ բիոլոգիայի վերջերս։ Տենց որ մինչեւ հիմա սովորում եմ որպես ուսանող, որովհետև գիտությունը դա շատ դա զարգանում է միշտ, it's a evolving structure, ոնց որ ասում են, եւ դրա համար
Պարոն Հայրապետյան, իրականում դուք կարող եք անգլերեն սկսել, որովհետև մենք բոլորս անգլերեն հասկանում ենք ու գիտեմ, որ ձեզ համար բարդ է հայերեն խոսելը, շատ շնորհակալություն։
Well, yeah, so the science is an evolving activity, and so therefore, in order to approach and attack a complex question in science, we need to work collaboratively with many scientists from different countries, with different disciplines. So therefore, the topic that I'm doing now and working on is an interdisciplinary. And let me share my slides. I want to start talking about it in case if you have no question. But if you have any questions about my, scientific life and the way I moved to the United States and started my life, we can please go ahead and ask me. So you can interrupt me at any time. It's going to be a very informal presentation. So friendly and informal presentations with a lot of videos. So I will try to inspire you to the questions that I'm really bothered with, and I can't sleep at night because it's very, very exciting. So you have any questions? If not, then I can start. Okay.
Yes, you can start.
Okay, very good. So let me then share my screen. So with my slides. Okay. Okay, so let's see. Do you see my slides?
Yes, we do.
Okay, so that's my presentation is titled as a jigsaw puzzle of life, how to detect a habitable planet. So you see in this picture two different objects. On the left, it's our planet, Earth. I remember when I gave a presentation at NASA Goddard for Whole Center, a public lecture, somebody who is not familiar with astrophysics or heliophysics asked me a question, what's this bug? Look at the left-hand side. It's like a bug, right? A person who is not familiar with astrophysics, and I would imagine that many of you are not. So I would imagine that some of you are computer scientists, some of you are chemists or physicists or astrophysicists or biologists, or might be even in humanitarian science and journalism. So the first idea that comes into mind is like, it's a kind of a bug, right? A bug-like structure, and on the right-hand side you see an object which actually is our sun. Okay, so that's our sun in very unfamiliar light. It's called extreme UV, extreme ultraviolet, extreme ultramанушака UV light. I put it together just to show how intimate is the relationship between our sun that we enjoy every single morning all the way to the evening and our planet. Believe it or not, it's not just the light that we get. It's not only beautiful sunrises and sunsets that we enjoy. It's much more. Our sun can be beautiful, but also can be a very dangerous beast. So therefore, if we want to talk about a habitable exoplanet, if we want to look for life in the universe, we want to understand, this intimate relationship, intimate connection between our planet, because that's the only planet with life, right? So we don't know anything else. We're looking, but we're sure that so far we have only one habitable planet, our Earth. And And so this our Earth lives under the sun. And only about maybe 50, 60 years ago, we started to realize that our sun affects many aspects of our life on Earth, not as a single, not at the level of a single family even, but the planetary scale. And so one question that I will discuss, that our sun can create global events that can be bigger than pandemic, coronavirus pandemic. So that's why this question is so important to understand first this intimate relationship, and also how other stars may affect their planets, exoplanets. Exo means that planets, extrasolar planets, planets around orbiting other stars. Okay, so that's what the exoplanet means. So exo, yeah. So in order to, so therefore, the big question that I want to ask today, it's very ambitious questions. Are we alone in this universe, and how common is life? That means that how unique is our Earth and life itself? It's a big question, right? So many philosophers ask this question over thousands of years, and people, arrived at different answers, different views, religious views, scientific views, and still under debate. And the only way to address this question, to uncover some aspects of this question, is to do, science, to perform science, to come up with testable predictions, and then to apply observations in order to prove them. So that's the only ultimate way to prove something or disprove. It's not that I believe so or I have a dream about this, but to say whether our theoretical views can match, can be tested and by actual observations. In this case, I'm talking about astronomical observations. So therefore, we need telescopes. The bigger, the better. And now we're lucky, and you're young people are very lucky that you live in 21st centuries, when we have a number of big projects that allow us to observe the universe at extremely high resolution. It's a spatial resolution. We can resolve structures. For instance, now on the sun, we can resolve structures, you wouldn't believe it, as small as about 20, 30 kilometers. I mean, the sun is at the distance of 150 million kilometers, and believe it or not, at such a distance, you can resolve extremely small structures. Of course, the further you go, the larger the scale, but still, we are now equipped with the interesting and very sophisticated equipment that can allow us to look at remote objects and to test our theories. So the one thing that I need to say is that just last month in last July, we had three launches to Mars. So our planet is habitable, but now we are actually believe that Mars may be habitable. So the Mars is the next, it's a red planet which is next to us. So we have a lot of reasons to believe that. You may ask questions later on, because I'm also doing Martian science, but I'm not going to talk about it. I will mention a little bit, because so many things to talk about. And so now we have three missions now on their way to the red planet. So I'm talking about the first Arab mission from the United Arab Emirates, from Emirates. It's called the mission called the Hope, Al Amal in Arabian. So now young Arabs are trying to also revive the space science after so many centuries of inactivity. But now they're becoming really active, because the Arab science astronomy was active in 6th, 7th century, and now we're trying to help them to understand the planetary the atmosphere of Mars. So they launched a mission to Mars, and in about 8.5 months, their mission will reach the planet. And then a few days later, a Chinese mission was launched, and so also to Mars. And so they also will perform complementary studies, and I can talk about that later if you ask a question or two. And the third mission, that was the NASA mission, our mission. So it's called Mars 2020. So it's a big rover, with the size of a bus. Okay, so it's a third one now, and Perseverance, and it has many interesting goals and experiments to perform, and the most important thing, to bring samples, Martian samples, back to Earth in a couple of years. So therefore, we are really at the brink of very exciting time, transformative time. So, and you should feel lucky to be born in such interesting time when we're asking those questions: are we alone in the universe? So in order to understand this question, we need to work together. So astrophysicists, heliophysicists, helio means solar, the basically helio from Greek means the sun. So the solar relations, of our sun with other planets, with Earth, Mars, Venus, and other planets. And then planetary, it's a PLN, planetary science, basically trying to understand Mars, Venus. So because now we also have some ideas that Venus was habitable way back. Okay, so might be life started 4 billion years ago on all three planets, on Mars, Venus, and Earth, but it only survived on our planet. If it is the case, why? That's the question we want to ask. How sensitive life is to different conditions, and what controls, what factors are important in controlling those conditions. So therefore, when we talk about habitability, we want to understand this, the puzzle of life. We want to put together all those pieces together, right? Some of them, as you can see, we have some pictures, we have some the pieces of the puzzle. Some of them are missing, but the most important thing that looks like that we're starting to get the global picture of life. What do we need? What kind of chemistry you need in order to form a primitive life form, at least. So we can look at the DNA, human DNA, the DNA of a plant, DNA of an animal, and try to find the most important building blocks existing everywhere. So the DNA molecule or RNA molecule, and then trying to understand what kind of molecule are we dealing with, and how can we recreate this molecule in laboratory conditions? If not, might be, can we recreate some building blocks of a molecule, because it's pretty, complicated molecule. So that's the question that also is immediately important to understand if we want to search for a planet like Earth, okay, second Earth or Earth-like. And, we shouldn't fool ourselves that, we will find exactly the planet like Earth with a lot of, humanoids and like in science fiction. Well, it would be nice. Yeah, I wouldn't mind. Like on Star Trek Next Generation or Star Wars, and some of them are hostile to us. Well, but if you want to put it on the little bit more kind of firm ground, scientific ground, it becomes a little bit boring, but not less interesting. Specifically, I say, well, can we find a planet with a primitive life, with the form of viruses and bacteria? Okay, so And even the question is a virus. Is a virus is a life form itself? Is now a matter of a debate, among the biologists. Some of them think no, bacteria, that's the form of life because it's kind of like a independent unit. But the virus needs a host. So the coronavirus also needs the host to get into the cell and start to multiply. Anyway, so the central question is, are we unique? And in order to find this question, I want to discuss those three different sub-questions, smaller questions. So we need to understand how did life form and evolve on early Earth, okay? Because that's the only planet that we know again. And we know that the life started on Earth 4 billion years ago. So, and so we have the ancient rocks. So we have the biological signatures of the organic carbon that tells us that at least 3.5 billion years ago, that's for sure, and 3.7 billion years ago, that's as far as we can go. And now other lines of evidence suggest that it might even go like 4 billion years ago. So therefore, the question is, why 4 billion years ago? Is there anything special about 4 billion years ago? Could have life started now? I mean, if we sterilize everything, let's say, imagine this mental experiment, you sterilize life on our planet completely, kill everything. Or imagine not even kill. I mean, you don't imagine that you don't have you have a planet like Earth with no life. And how can we imagine a life can start? Because we see different stars in our galaxy, and whether we want to find out, what stars we want to look at. I mean, what kind of planets we're going to look at that will resemble our Earth. So the second question is that, what's the role of the young sun? I mean, the sun was young, the Earth was young, but our star, the sun was also young, and now we have a luxury to observe a lot of young stars, okay, like our sun 4 billion years ago. By the way, when I was admitted as a graduate student at Burakan Observatory way back, I mean, that was one of my questions, to understand young stars, active stars. So that's how I started my science, without even thinking that time, over 30 years ago, whether the study of young stars can be related to uncovering the conditions of our young sun, okay? Because sun is a star, believe it or not. So, but I only understood that only a few years ago. And now I'm trying to reconstruct the life of the young sun by looking at other young stars resembling our sun in many ways. And the last question: how can we detect young Earth? Okay, so because you say, well, if life started 4 billion years ago, so can I go and find a planet as young as our young Earth at the time when life started on Earth? Can I find the planet, pregnant with life? Not just life itself, but some kind of a, process of initiation of life. That's the one, the view that I take. Because I say, well, life can take different ways. It's like a tree. You can have a first a single branch, right? And then from a branch, you can have many also other branches. So I say, well, the branches can grow in different ways, and each sub-branch might be another manifestation or realization of life. And life can take different forms, very unfamiliar forms, unknown and wild forms, even wilder than you see in sci-fi movies. But I believe that the start of life should be universal, while the life itself can take many different forms. Look at you. When you were babies, you were all basically the same, right? Especially in the first few hours. But later on, your life started to diverge. And now we're dealing with the 7.5 billion individuals on our planet, and every individual is different in many ways, right? And lifeline is different. But I want to go back at the time when everything started, to the beginning, because I believe that was kind of like, maybe we will be able to find a universal answer to those big questions. So, to start this, I want to introduce our cosmic home. So, yeah, I know that you live in Armenia, it's a beautiful country, and my home too. And this Armenia is one of the countries on planet Earth. The Earth is the part of our solar system with 8 planets, excluding Pluto. But I like Pluto. I wanna have Pluto back. It's a very interesting planet, by the way. Anyway, so it's our local neighborhood. It's our so-called solar system. It's our sun and 8 or 9 planets, depending how you handle it. That's our local home, I would say. A little bit bigger, but still local home. Okay, so and the light propagates in 8 minutes and 18 seconds from the sun to us. So that means that whatever you see on the sun, happening on the sun, a flare or some kind of big explosion, occurs 8 minutes and 18 seconds later. So it's kind of like a small time machine that you're looking, back into the past. So, but if you look at our sun and the solar system, we now realize that the solar systems or stellar systems are very common. Actually we live in a bigger home, than a country, than a city, than a country, than a planet, than a planetary system. It's called a galaxy. And our galaxy is called the Milky Way galaxy. And if you travel to Burakan Observatory or any on Diligent or any beautiful location at night, a clear night, you see a lot of stars, right? And if you don't have any city light, you will see this milky, stripe. It's called Milky Way. So this is one of the arms of our galaxy, our home, a home of 200 billion stars, with about 10%, exactly 8.5% of stars like our sun, and 3/4 of it stars that are very, very unfamiliar and very different from our suns, called red dwarfs. Okay, so they're much smaller, much dimmer, and much cooler than our sun. So the one question that you may ask immediately and realize that our sun, well, it's about 10%. Every 10th star in this big galaxy, as you can see, is like our sun. That's the first clue. So you say, well, yeah, we have a lot of stars. It's 200 billion, 10% of it, you can immediately understand. So 20 billion, right? 20 billion stars in this home is like our sun. That's one thing that you learn. And at the distance of, we see that 100,000 light years. The basic light takes about 100,000 years, to travel from one age of our galaxy to another. And then you look at the universe, you see so many galaxies as our spiral galaxy, Milky Way galaxy. By the way, it's like 3/4. Every 3 out of 4 galaxies are like our galaxy. That means that our galaxy is like a common guy on the street. I mean, you would basically find it practically everywhere. And that means that, and you would find star like our sun also pretty everywhere. So that then we say, well, that might be the some kind of a clue why we are around our sun, because it's not like hot stars that you see 1 out of 100 in the galaxy, but it's 1 out of 10 in the galaxy. Okay, so Now, so that's our local home that I was talking about, cozy home with the sun, which is unfamiliar because you never seen the sun such a, with a bizarre light. It's called X-ray and extreme UV light, which is extremely important for our conversation today. So this is basically the emerging picture. Now, imagine, since 1995, with the detection of the first planet orbiting or circling around a star like our sun, it was detected, by two American astronomers and Michel Mayor in Switzerland. So, by the way, there was a big controversy who was going to get a Nobel Prize. The Michel Mayor got a Nobel Prize, but the two American astronomers from University of California, Berkeley, detected the first exoplanet, but they couldn't understand. They detected exoplanet that I was told by one of them that they detected a signal from a planet like a Jupiter, a huge giant planet, okay, orbiting a star like our sun. But for Jupiter takes many 240 years to orbit, to complete one orbit. It's pretty far away, from the sun. But this planet was revolving every few days. They say, well, it cannot be the case because Jupiters are so far. They should be pretty far because we know that from our solar system. Imagine that's inertia of how people think, right? Of thinking. So people say, well, that's what I know. I know our solar system. Jupiters are far away. If I see a Jupiter-like body, a planet or something, an object, that cannot be a planet because it cannot be Jupiter. And then they didn't publish it, but they discovered it first. So by the way, during the presentation, Nobel Prize presentation, they showed the picture of Marcy and Butler, two astronomers from Berkeley. Actually, that was a little bit bizarre situation when Michel Mayor gave a talk. Actually, he got the Ambartsuman Prize at the observatory recently, a few years ago. Yeah, not recently, a few years ago. Yeah, anyway, but since that time, due to the observations from the ground and also the Kepler Space Telescope that we're going to talk about later, discovered thousands. So now we know, can you imagine, from 8 planets in our solar system, we moved to 4,000, over 4,000 planets around other stars. It's really a revolution, right? So now we have so many dots. Every dot that you see here, of different color, is a planet orbiting some other star. Okay, and so I'm not going to go into the technical details how they will discover. If you're interested, then you can read about it: the radial velocity, transit, imaging, microlasing, pulsar timing, and Kepler telescope. But what I want to say, this red. This red curve shows you the planets like our Earth, with the radius of one Earth radius. The one, you see that it's basically on the vertical axis. It is kind of all exoplanets with the size of our planet, and on the horizontal axis you have the rotation period of those planets around their host star. Okay, so we are at that 1 year is 365 days, right? There's 200, there's 300, 365 somewhere here. So that's our Earth is somewhere here. But you can see all detected exoplanets, this one, all those like Earth, are revolving much, much closer. The question is that, is there any kind of, does it mean that our Earth is unique? Because we don't see any planet, revolving at such a distance like we are from the sun, revolving at the rotation period of 100 days, for instance, or 200 days, 300 days. Why they're so, close to their host stars, see? Like revolving at 10 days, it's 10, 20 days, might be 30 days, might be 32 days max. But the smallest is like 0.5 days. So the question is that, is there something crazy is going on? Why is that? But the answer is that our instruments are not sensitive enough now, but we're getting there. So it's becoming better and better every day. And James Webb will make a revolution. I will talk about that later on. That we will eventually get to the point of finding this and filling this gap. Okay. So now what you see here is that the different exoplanets. See, this is the whole symphony. This is our solar system, and so you see, we don't show here the central star, but exoplanets revolving around their stars. You can see that some systems have 2, 3, 4, 5, 6, 7 exoplanets. Okay, like in our solar system. This is a zoo of exoplanets. So therefore, if we want to understand and look for habitable planets, now we have some material to deal with. Okay, so this is the important point to mention, that we have observations, and if we have observations, so there we're talking about science. Science starts not with speculation, but starts with observations. So that's why, after we discovered so many exoplanets around other stars, over 4,000, we have a scientific basis to talk about astrobiology, to talk about finding life. So it moves from the area of science fiction, Star Wars and Star Trek, to actual science, to actual NASA science and international science. Okay, where government is willing to spend, billions of dollars, and NASA budget is $20 billion, by the way. So significant amount of money spent on basically addressing this fundamental question, whether we are alone in the universe, where we can find life around other stars. So in order to find life around other stars, let's look at our sun. So this is the sun in very unfamiliar light. I would imagine that probably, majority of my listeners, of you guys, never seen our sun in this unfamiliar light. Normally you perceive it as a yellow object, and now you see kind of like hairy thing, right? So with the brighter regions and darker regions, with some bizarre thing, and some of the you see here brightenings. It's called the solar flares. Okay, so this is basically the explosions, the cosmic explosions of gigantic proportions, with the hundreds of millions of nuclear bombs per second. Okay, so it's a huge amount of energy released by our sun, and those kind of explosions, affect our atmosphere, the atmosphere of our planet, and that we realized that only recently. So therefore, we want to study, we want to predict, we want to monitor, and we want to know what is going on with our sun when the next big flare will occur and will, affect us. So one of the events that occurs on our sun that basically, accompanies these flares are so-called coronal mass ejection. So when those the flares, those big explosions, release of energy, huge amount of energy, catastrophic release of energy, also is accompanied by the ejection of the material from the sun, from the hottest region called corona. Okay, from the corona. It's don't confuse the corona with coronavirus. So the corona is like crown-like corona. Basically, it's a geometric resemblance. But our sun has a corona, and this corona is so important in order to understand, because it's a cradle, it's a site where flares form, And also, when the flare is energetic enough, it can eject also, hundreds of millions of tons of material with it into the outer space. Yeah, I'll show you the picture. Yeah, you see this big explosion, and so this is in the center. You see that our sun, and let me show you again, explosion, and then you see the ejection of this cloud, and then you see a lot of noisy stuff, all those dots, right? Dots are particles, energetic particles accelerated by the propagating, ejecting material. And we're talking about these clouds move with a crazy speed up to 2,500 kilometers per second. So basically they're so fast that in about 11, 12 hours, the fastest ones can reach us. Normally it takes about 16 hours. So that means that if we detect something like that, the cloud moving in our direction, we have only maybe half a day in order to do something about it. Okay, so that's this kind of event, and the flare, coronal mass ejection, energetic particles are called space weather. So it's kind of like a weather, in analogy to our meteorological weather on Earth. So you watch TV news when they report the models, of atmospheric models of atmospheric scientists who predict the climate of our planet and weather. So basically, it's much more shorter scale atmospheric processes in your local area. Let's say in Armenia, what would be the temperature, pressure, humidity, and the wind speed, right? That's what you want to know, to plan your day, whether it's going to be a big hurricane or going to be a nice sunny day. So that's why we also want to know whether it's going to be a nice sunny day on the sun. A quiet day, I would say, sunny from that point of view, without those big explosions that come and go every 11 years, so-called cycles of the magnetic activity. So those events are now catching more and more attention, and you see those journals, the Sky and Telescope, and Science magazine, and different magazines and newspapers, when talk about space weather, and the space weather is basically because they affect our planet, they affect the atmosphere of Earth, and can create a lot of bad things, like the interaction of this big clouds with the magnetic bubble surrounding our Earth, called magnetosphere, can induce electric currents. So we'll talk about that later. So basically, this is the picture that shows how intimate is the connection between our sun and the Earth. You see, this is our sun, that it basically from time to time forms those big explosions, eruptions called flares, and then they come also with the ejection of those clouds, gigantic clouds of the material and magnetic field, called CME, or coronal mass ejection, the wind, and particles. You see those yellow particles. So if they are oriented toward our planet, they can hit this bubble called magnetosphere. So our Earth is surrounded by the magnetic field. Okay, so magnetic field is one important part of habitability. It's a shield. It shields us from the harmful ionizing, radiation coming from our sun. So that's probably why Mars has an atmosphere 160 times thinner than we are, and doesn't have appreciable magnetic field. So Mars, in a much worse case from that point of view, the surface of Mars is sterilized by those energetic particles. And our surface is not sterilized, because most of those particles that entering the atmosphere, through those gaps, along the magnetic field lines, are being stopped by the atmosphere somewhere at elevations over 10 kilometers. So, and during those big flares, by the way, when you take this long, flight, for instance, from Armenia to Los Angeles, or to New York City, sometimes you go over the polar, close to the polar region. Okay, so that's this kind of a curve. It's much more economical from the point of view of fuel consumption, and so you go from that point. And if you are unlucky, then and you fly during those big event of flare with energetic particles, with energetic protons, those energetic protons can basically go through the airplane and through the human body and can destroy DNA. Most of the DNA repair itself, but if this event is too strong, it may cause some irreparable damage and cause some cancer. So therefore, it's the important point to know and to predict, when we have an event and how we can mitigate this problem. Okay, so this is the picture of how those big events interact with our atmosphere. So this is our Earth, the blue planet. This is the magnetic bubble around it, magnetic field around it. It's called magnetosphere. And now from the left, you see the magnetic cloud coming in. See what it does? It squeezes the bubble. The bubble becomes smaller and smaller. And these particles can penetrate in through this open region in some polar areas, in the region around Alaska, around Arctic Pole. It's typically about 77 degrees latitude. Okay, so these numerical simulations that show how they interact. So this is basically the picture that shows that every time we have a big flare on the sun, it basically also ejects the huge material. And if this big cloud, coming towards our planet, the blue planet, the Earth, the particles can also accompany it, and they can penetrate in and affect a lot of things. So the way it works, and this movie shows, this magnetic field interacts and basically reconnects, ejecting this material. This material, magnetic cloud, the CME, travels to our planet. Okay, if it travels, because they're pretty wide. In many cases, they hit us. So then the magnetic field of this cloud interacts with the magnetic field of our planet. It basically destroys the magnetic shield partially. See what happens. And then it forms particles that penetrate in. And then the day side, so that's the day side, and then on the night side, that's another way to reconnect. So this is called the space weather. And we understand the space weather now, in a good way to start addressing the question how it can affect other planets. So the extreme events happened, the Carrington event, in 1859, over 150 years ago, one of the biggest flares, okay, when you could see aurora or northern light, that normally you see when you visit, Arctic regions, like north of Russia, or when you visit Siberia, north of Siberia, or if you go to, Yakutsk, or you go to Alaska, then you normally see those events, this beautiful aurora borealis. But it turns out that during this event 150 years ago, people living in Miami, okay, close to equator, they observed the corona borealis or northern light, aurora. So this aurora can be observed, let's say that if the magnetic field is broken for some amount of time, might be for a few hours, then particles can penetrate at lower latitude, and so forming those beautiful events that can be observed, practically all over the planet. So the question is that how common it is, how other exoplanets can they be also exposed to those kind of flares? And those surprises come from the Kepler mission, which is now already not operating. It was retired a couple of years ago. So we now have TESS mission. And the Kepler mission was like about 90 centimeter telescope. It's like a mirror space telescope, but looking at one, part of the sky. Imagine that if you sit, you look at a person, okay, at one person for 4 years. No lunches, no breakfast, no lunch, no dinner, no vacation. So you cannot go out from your seat. So you're still on your seat. You sit and stare. Look at this person every single second. You imagine how many different mimics and different information you can get from the face, from the facial expression of a person, right? You can ask questions. The person can smile, cry, get tired, sleep, wake up, but you're looking at it just, at him. That's exactly what this telescope did. He, over the 4 years, looked at the part of the sky, and each pixel was looking at one, star with the exoplanetary system. Detecting this light changing, stellar brightness changing as a planet basically transits the star and changing its basically line with variations. So monitoring 150,000 stars, at 1-2 minutes to up to 30 minutes for 4 years. And that's what was extremely important in finding the 4,000 planet. Now it's not planet candidates, but exoplanets around other stars by looking the transits as they transit over the surface of a planet. So as they do, so we have them also transits of exoplanets, but also have them, star spots, those big spots that you could see, you saw on the sun. Okay, let me go back here. Here. Yeah, some of those regions, here, they form from those regions associated with dark spots on the sun. It's called star spots. So this is the one of the big star spot. This is the star spot from the Carrington event that basically was the site to form a flare. It's a region of a very strong magnetic field that provides energy. So, and you see from many stars, that was also another evolution, not only detects exoplanets, by Kepler, but also detect those spikes. See the spike, one spike, this spike, this spike, this spike. Many, many spikes, that's just one star. And this is the rotational modulation created by star spots, big star spots on young stars. And we're talking about stars resembling our sun 4 billion years ago. So now we're getting to that point. We're looking at the sun in its infancy, and we are now realize that, and so this is only the few days, and you see that in a few days, like 10 days, you see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So about 10, 11 flares occurring in so many days. So it means that this, the young sun was flaring pretty frequently. So it's was forming those big star spots. That's the star spots that I'm talking about. The star spots as they move, from left to right, let's say, as a star rotates, so it comes and goes, right? And then star spot goes on the other side, the star becomes brighter without the star spot. When star spots come in, becomes less brighter. So therefore, that's how you can see it. And this is the star with the flare. This is the big flare. This is without flare. Okay, those big events that are 1,000 times as bigger, stronger, more powerful than the biggest event from the sun we can observe today is called super flares. So the super flares were pretty common, on young stars. So this is the sizes of the star spots. That's the star spots for comparison that we observe from the current sun. This is those small dots. You see the small dots. So that will happen when the flare will be like 10 times bigger, 100 times bigger, 1,000 times bigger. So that's how you can compare those star spots with the sunspots. Okay, this is sunspots from the big sun, from the young sun. This is the sunspot from the current sun. And the question is whether something like that can ever happen, tomorrow, 100 years from now, 200 years from now, 1,000 years from now. Can our sun create the superflash? Because if something like that happens, due to this interaction of this magnetized blobs of plasma that I showed, it can create catastrophe on our planet, and it can end civilized life. I'm not saying that it will end all life, but it may end all civilized life. Electricity, kill computers, erase memories, and so on. And again, we can talk about that later. So this is the first simulations to show that how this is the magnetic field of the young sun, resembling our sun 4 billion years ago, and you can see that the magnetic field changed in just a few months. This is 2 snapshots of three-dimensional computer simulations of my team that we created to show that how the solar twin will look like, looked like, I would say, 4 billion years ago. It is important because we want to recreate those conditions in order to understand what kind of emission our sun, our planet felt. Another thing about young sun to know that even though the young sun was very energetic, but it was actually fainter than today, about 30% fainter. So our sun was a faint star. It was active with a lot of flares, but I mean, in terms of the total amount of heat that it can produce is about 30 times less. That means that instead of having a wet and warm planet, we're supposed to have a cold and icy ball, but it wasn't the case. So we would expect that the faint star gives you the faint planet, but it wasn't the case. And so this is called the paradox, it's called the faint young stars paradox, that you would expect the cold, but it wasn't cold, it was wet. That means that something was responsible for heating it. And the only way to solve it is probably greenhouse, gases. Some kind of gases were present that were trapping this, the outgoing radiation from the sun. It's like today we have global warming, right? But that was what I would say mega global warming, at the bigger scale that you need to trap the infrared radiation from escaping to outer space to hit but that way to create kind of like an envelope around it to preserve the temperature above 0 degrees Celsius, at which water can be in a liquid phase. Okay, so because you need liquid water in order to have life. So this is basically our reconstruction of those giant explosions, magnetic coronal mass ejections. So you look at our sun at the North Pole here. You look from the up down, okay, and that's the ecliptic plane of the. So let me show you again. So yeah, and then another picture you see where that's where you're facing it. So you're looking at Earth. So from Earth, and you see how the cloud approaching you, and eventually hits the magnetic field and can break the magnetic barrier called magnetosphere. Okay, so this is basically the situation when the magnetic field is broken. Where you see this, you see basically no field here. This is the facing the sun on the left. So therefore, those events can happen, but they can create an opportunity for life, because if something like that happens, the particles can penetrate in and create the showers of particles. Those showers, when this energetic particle gets in, it can ionize species and create the showers of other particles, pions, muons, electrons. And it turns out that those particles, those non-thermal electrons, for instance, they play extremely important role in starting a very, chemistry of an atmosphere. So that was another process of the atmospheric escape when, our early Earth was a volcanically active planet producing a lot of carbon dioxide, volcanic gas, producing sulfur dioxide, SO2, hydrogen, water vapor, but it's mostly water vapor and carbon dioxide. But then the interaction of the UV emission of the sun, extreme UV emission with those gases can create atmospheric escape. So our simulations show that created the Earth with the atmospheric pressure about, at least half of what we enjoy today. So this is the particle cascade that creates many particles, and you're here, a happy observer on Earth. But imagine that at a time when you weren't around, we only had, the Earth was basically a sterile plate with no life. And the question is that whether those particles can induce some chemical reactions that can create life. And then if you ask if you ask yourself, so what is the chemical composition of Earth today? It's a 77% of molecular nitrogen, right? And it's about 21% of oxygen. And again, oxygen, it's just the latest invention of our planet. It wasn't around 4 billion years ago. It wasn't around 2 billion years ago. It just started to accumulate about 2.5 billion years ago, with the current proportion just recently, I would say, only about 1 billion years ago. So therefore, it's not a typical thing, oxygen. But so the first life was without oxygen. We know that. It's when the bacteria absorbed the carbon dioxide and emitted methane, so-called methanogens. The first life didn't need oxygen. Even some of the bacteria in your guts, in your stomach, and in swamps, we see those bacteria that don't know anything about oxygen. As soon as you take them out to the oxygenated atmosphere, to the current atmosphere, they die because they don't know how to deal with oxygen. They probably were formed first, 4 billion years ago, when Earth didn't have oxygen. It has only carbon dioxide from volcanoes, water vapor from volcanoes, and nitrogen from earthquakes. A lot of frequent earthquakes. So the earthquakes and volcanoes were extremely important, to produce an atmosphere that we enjoy today. And the question is, why we have so much nitrogen, 77% of nitrogen? Why not 7%? Why 77? Is that important for life? The answer is yes, because if you look at every molecule, DNA, RNA molecule in your body, that, as I said, creates this kind of like the building block of the cells and of all living organism on our planet. Nitrogen atomic nitrogen is extremely important. But the reason why 77%, because the molecular nitrogen, I'm talking molecules, is when the two atoms are bound together. Atomic nitrogen gets together to create that, the happy family of two atoms called the molecule, nitrogen molecule. And so in order to, but this molecule, because they're bound, very strongly to each other, they like each other. So you need to apply a huge amount of energy to destroy them. The only way to do it is like apply UV light, extreme UV light, or energetic particles like electrons. Unless you have them, you cannot destroy them. So that's why if you don't have any flares, any other source of energy, of this extreme energy I'm talking about, then these two atoms, they will be bound by this triple bonds, chemical bonds with huge amount of energy, like 10 electron volts, and they're very inert. They don't like to talk to anybody. So the N2 will just exist by itself for billions of years. Okay, so that's why we had might be 80-90% 4 billion years ago. Now we have 77% because it's so hard to destroy it. Okay, so once you create it, it's hard to destroy it. But so therefore the question is that how can you destroy it? Because as soon as you create nitrogen, atomic nitrogen becomes very chemically, friendly. And
The star show was much more violent than it is now, constantly erupting and sending out huge particle clouds. Young Earth was different too. It was still growing its magnetosphere, the magnetic shield that protects planets from the sun's forces. This weaker magnetosphere's polar caps were far wider than they are now. This let particles from the active sun seep into Earth's nitrogen-rich atmosphere. The solar particles split up the nitrogen molecules into atoms, and carbon dioxide in the atmosphere into oxygen and carbon atoms. The free-roaming oxygen paired with the nitrogen. The result was nitrous oxide, a powerful greenhouse gas.
Yeah, so it shows only the part of the movie. It's nitrous oxide, and also the second molecule that is created here is so-called the hydrogen cyanide. And the hydrogen cyanide is the, it's HCN. So the nitrous oxide, it's the laughing gas. When you go to the dental office, they may give you nitrous oxide. You get into euphoria. You start smiling. Having good ideas, might be not feeling any pain. So that's what it is. So the early Earth, when the life started, was pregnant with life, was under the euphoria, under the drug of nitrous oxide. So at the same time, those kind of chemical reactions that create those small molecules due to the destruction of the major molecules, due to the X-ray and UV light from the sun and energetic particles, they create those a little bit bigger pieces, CO, CN, NH, NO, NO2, OH, different molecules that then interact and create a little bit more complex molecules, N2O, which is a very strong greenhouse gas that can explain this faint young sun's paradox. It's 300 times stronger than the carbon dioxide that creates the global warming headache for us today. But the Earth needed that headache in order to keep water in a liquid phase. At the same time, it creates the hydrogen cyanide, hydrogen HCN, which basically, as you put it all HCN together, you put 5 HCNs together and you create amino acid. You create proteins. You can create, adenine, uracil, cytosine, guanine. I mean, you create these building blocks, nucleic bases of a DNA, RNA and DNA molecules. So, yeah, we don't go all the way to the RNA, DNA, but at least our modest goal is to recreate those molecules, to understand what kind of path, what kind of cycle do we need, to go from the sun, from the molecules in our atmosphere that you breathe in, of course, without oxygen, as I said, all the way to the building blocks. So this basically the emerging picture when the young sun can produce enough energy in order to metabolize and to activate the atmospheric species of our planet to initiate chemical reactions, then eventually can produce HCN, simple sugars, and building blocks of RNA and DNA molecules. So that's one of the pictures when HCN dissolves into clouds, and then it creates so-called formamide that gets into the earth and forms more complex molecules. So this is our simulations that called global climate simulations that shows that this predicted amount of nitrous oxide of this laughing gas can explain the faint young sun's paradox. Because we had two paradoxes. The one is a chemical paradox of life, how to create life from simple molecules, that you breathe in, and the second, how to explain that the liquid water was present, the temperature was high enough under the faint young sun's paradox. The faint young sun's paradox and chemical paradox of life should be resolved together. So from that point of view, once you have those, and we know that our sun was active for a few 100 million years, and if you put in more and more energy into those molecules, you can take them out of the chemical equilibrium and create more and more complexity. It's imagine that, you, without any prior, information, you go to opera, in Yerevan, Opera Square and the Freedom Square, and then you find 1,000 people there talking about something at night, at midnight. on Monday. Okay, so that for you will be a miracle, right? You would say, oh, it's a miracle. How can those 1,000 people get together without any prior information, without Facebook or cell phones? They just got there because just by accident. So the point is that if you have those, the external energy sources, it can create from one molecule, the pair 2 of them, and then 4 of them, and then 16 of them. You can create more and more complexity by taking system out of the equilibrium. So the life is a chemical tsunami. It's a tsunami of chemical molecules that needs to be powered by some process. Tsunami is powered by earthquakes, right? So the chemistry of life could be powered by the energy from the sun. That's basically the emergent point. This is our chemical experiments in Japan, that we started to produce amino acids from protons directly, by just throwing from dirt simple molecules like molecular nitrogen, carbon dioxide, and water vapor, and a little bit methane. That's all. And you start producing amino acids, glycine and alanine, in a lot of amounts. So basically, the cookies of life need basically the 3 conditions. You need the energy flux, like from Zeus. This, sending like lightning, or I'm talking about the sun, solar energy flares, and then you need the dough, cooking dough. And if you put together water, cooking dough, and some oven, right? That's all you need. You can create cookies. So the cookies of life is basically that's what it needs. 3 different ingredients. So now once we understand what the ingredients are, we can start discovering what kind of biosignatures we can think of, that can produce different molecules, most abundant ones, with the spectral fingerprints that can be observed with big telescopes. One way to look for life, it's basically alien megastructures, or to look for McDonald's, or to look for Starbucks, or Chinese restaurant on another planet, and say, oh, that's life. Yeah, well, that's one way. Or another way to basically look at the chemical fingerprints of molecules. This is what. So look at them, but for that you need big telescopes. That's exactly what we're doing. We're gonna look for this, absorption formed by those molecules as the light from the planet basically passes through to us. So, and by looking at those fingerprints, we can decode the radiation from those complex molecules that are needed in order to create life. So this is one of the spectrum. This is the Earth, okay, the one Earth from space, that shows you that that you can have the oxygen too, you can have CO2 in the infrared light. So that's why So this is the if you look at this is better picture. This is Earth, Venus, and Mars. You see the CO2 absorption. That's why because CO2 absorbs the infrared emission, at about 15 microns, that creates the global warming. But you can have nitrous oxide that can even absorb much stronger, can create, global warming right here. It's in red. So therefore, the strategy of life is either to look for intelligent life, which would be 10 to the power of 20. 1 and 20 zeros times less abundant than the bacterial life. So therefore, my bets are I want to go and look for those guys, and some people who do science fiction that can look for those guys. But well, we have SETI program also that looks for signatures too. And now NASA started to fund already those programs too, to look some kind of signals of intelligent origin. But my preference is this, because it's much more abundant. So I have more chances to observe something. Especially I have now different flotilla of telescopes, ground-based telescopes, 10-meter telescopes, and also the one James Webb Space Telescope will be 100 times as powerful as Hubble Space Telescope. It will like kind of float in space, and with the diameter of a mirror of 6.5 meters, it will have extraordinary power to look for the spectral signatures in the infrared band, in the micron band, the near to mid-infrared, to about 20 microns. That's basically the range at which those molecules emit organic molecules. I'm talking about molecules that constitute life that can be found. And that's our best hope. So my last slide is that the possible projects for current and future astrophysicists, solar physicists, chemists, and computer and atmospheric scientists in Armenia. First, it's the observational program. Now I'm carrying out this, big program trying to understand the life of the young sun. So we're starting this project, the Burakan Observatory, trying to, observe. So now I have a program with the Hubble Space Telescope, X-ray telescope, so-called XMM Newton, and then this cosmic telescope, so-called TESS, Transiting Exoplanet Survey Satellite, and the spectropolarimetric observations in Pic du Midi in France, and the Burakan Observatory observations, photometric observations, with even small telescopes, can support all those observations together, to answer the questions about those big star spots and flares. So because we want to know, that if the planet has too many flares, then that makes life impossible to make. So you need flares, as I said, to have those particles that can then catalyze molecules into more complex molecules. But if you have too much extreme UV emission, then the atmosphere will get evaporated from the planet, killing atmosphere, reducing the pressure, making life impossible because the temperature will go down below zero. And the second project is computer simulations. That's for computer scientists, or people who understand Fortran or C, C++, and a little bit physics or chemistry. It's identifying organic chemistry of exoplanetary atmospheres modified by active stars and models of atmospheric biosignatures. Thank you very much. I'm sorry for a lengthy presentation, but I was trying to give you a little bit of a picture what is going on. Thank you.
Okay, thank you very much. Actually, we have a few questions. One of them is in Zoom, if you can see them. If no,
okay. In this case, I have to stop sharing, okay, to see those, because otherwise, okay. So I'm going to the chat. Okay, so
Maher wrote about yes, you can see.
Yeah. Is Hehine Ayvazyan is here?
Yes, but not that one. Maher, is there a collaboration between universities here in Armenia and your university for these topics?
Well, so not yet, but so we are starting a collaborative effort between Burakan Observatory and NASA and American University. So now Burakan Observatory assigned me as a subject matter expert at Burakan Observatory, where I would have an opportunity to work with the young scientists specifically for those observations. Okay, so on using small telescopes, and I sent a photometer from the United States recently, just before coronavirus started last year. And so we're now thinking about how to adopt it and put on a small telescope and to use the help of, students, undergrad students or grad students can be taught how to do observations, because they're pretty simple. And then how to use the simple computer programs in order to decode the photometric signal, to understand what you're observing, how many flares you observe from those stars resembling our sun 4 billion years ago. But but I'm looking for more collaborative efforts. I will be happy to.
That is very interesting. And can we ask you to turn on your video in case that?
Yeah. Sure. Yes. Oh, of course. Sure. Sorry. Right. Yeah.
Thank you. So there is another question here. So Siranush Asadrian is asking how you managed to join NASA.
Okay, so how I managed to join NASA. Actually, yeah, as I said, I was at Los Alamos as a postdoc for 1 year, and then I applied to different universities. To do science. Science is very competitive business, extremely competitive business. People think that because every country allocates certain amount of money for scientists, right? And too many people want to be scientists because it's really inspirational thing, right? It's the mind-boggling thing. Yeah, but unfortunately, in order to basically proceed, especially in the United States and in Europe, only 1 out of 10 people get grants, get funding for science. So for that, you need to write a proposal that basically creates the compelling case. Why do you want to study what you propose to study? Why do we need to pay you salary of a scientist? Why we need to give you money for conferences? And how do we know that first that the topic that you suggest is important for the world science, how other people will benefit from your science, not only you, because you work for other scientists. So if people don't refer to my papers, if they don't cite my papers, then I'm doing bad job, right? So I work for the community. So if people are interested in what I'm doing, the more people interested in my work, the more successful I am. The more funding I will get for younger people, in the future, in order to support not only myself, but other people, my team. So basically, I applied to NASA Goddard with the proposal that if they hire me, what I would do. It's like, the JFK, Kennedy said, think about not what your country can do for you, what you can do for your country. So that's what my logic, what I can do to NASA if they hire me, because the competition was 1 out of 200 people. Okay, so you're competing with other 199 people who wanted to get this position. I'm talking about back to 1995. So, and when I was invited for an interview, so they basically selected three candidates out of 200, or around 200, as far as I remember. So then they invited me, and they had an interview for the full day. And they said, okay, so, we got this specific group that had funding from Hubble Space Telescope. I became a scientist to try to understand, very strange data from Hubble Space Telescope. So as normally scientists say, oh, we want to have more data. But once you get data, you see some strange things that you cannot understand. You say, wow, I didn't expect that. And Hubble detected certain signatures, spectral signatures, from stars that our sun will represent 6 billion years from now, old stars, so-called giant stars. And these stars showed the very crazy features, and they asked me a question, if we hire you, how can you explain it? What can you do with this? Because, every person who they hire, NASA hires, or any other big, good university, they want to bring a unique person with unique perspective, with unique skills, So, and then I said, well, I think that I can explain it. I did my homework because I knew that they presented a paper with the first observations from Hubble a few months before they hired. So I looked why they're hiring, the first question. And then I realized that, well, they have some kind of exciting data that needs to be understood. So I went to I approached the Blackboard and started to explain what I think. They liked it. So basically, what they were looking for, not only my previous papers and not only my experience, but what I can do in the future. Okay, so that's how I started. And so working, honestly, 12, 16 hours a day. That's what the young scientist should do, should work really hard. Because if you're passionate about the subject, I'm still passionate today as I was 30 years younger, and I still work 12 hours. sometimes. I paid for 8 hours because scientist never works for salary. It works to satisfy its curiosity, right? Getting funds. Getting funds from the government. but you need to justify this. So basically, that's how it happened. I was hired in the astrophysics division at NASA Goddard, and then I moved to heliophysics division because I realized that those stars, but I have a star next to my door, right, next to my office. It's our sun, and I don't know anything about it. I mean, talking about professionally speaking. So I started to write proposals. What can be done with studies of our sun. So I got another grant from the solar. So I was working in 2 divisions, in solar and astro. And then later on, when I realized that the sun is a star, it has those kind of flares and coronal mass ejections. We got first-hand experience. How can I apply computer models? I said, well, now I can move further to understand how the sun and stars affect exoplanetary atmospheres and the chemistry, And then, so I started to work with chemists. Now I'm working with chemists and biologists. So basically, that's how a project became more and more interdisciplinary and more interesting. So I'm still there and expect to be there for another, might be 20 years or so. Scientists normally pass away in their offices. So I'm not planning to retire anytime soon.
We hope so. Thank you. There is another question from Milena Safarian. So she is writing, thank you so much for an interesting lecture. You say that NASA rover would bring some samples of life, but what do you think? Will it be dangerous for our planet to bring life samples from different planets?
Extremely good question. Yeah, so it's called the Planetary Protection Program that we have at NASA. When people are thinking about, contamination, the first question is that if we contaminate the Mars, let's say, with life, because, as I said, that the surface of Mars is now sterilized with those energetic particles and extreme UV emission and UV emission. UVB, UVC emission, but because this mission, Mars 2020, will have a drill. It will drill, below the surface. It will go down to about 3 to 4 meters. And now observations of Mars show that from time to time we have the burst of water, from the caves underneath the surface. And the water comes out to the surface, those sandy barhans, the sandy dunes, and changing the pattern from this beautiful, like a Sahara, showing some kind of disturbance that can only be created by water and immediately evaporating because the pressure is too low. Okay, so when it happens, we understand that the water exists in the liquid state, below the surface. If water is there, the pressure is much greater. The bacteria, if they started 4 billion years ago, the same way that started on Earth, they could have been preserved, still. So therefore, we will look for them. So now the question about, is it dangerous or not? Now imagine that, on our planet, if we bring another bacteria, you saw those crazy movies when those bacteria start to eat up, and destroy our planet. The point is that I don't believe personally that that's dangerous because, over the 4 billion years on our planet, bacteria, they found an equilibrium. They talk to each other. They live, they occupy all those biological niches. They occupied all those, different floors on this big building of life. So some bacteria live on the first floor, some on the second, some on the third, and they don't step into each other's life. Some of bacteria are used as a food, some bacteria are used as a prey, right? Some of bacteria are victims, and there is an equilibrium. Even in your body, you have a few kilograms of bacteria, bad and good, and you need bad and good bacteria, because they do their work and they work together, to create a complex organism. So now imagine that you bring a bacteria, that evolved 4 billion years on Earth, but doesn't know anything about the biological niches of Mars. You bring them to Mars. Of course, the bacteria on Mars over the 4 billion years ago were happy with their own life. It's different, strange life, but their own life, Martian life. And then somebody, from Earth comes into, I'm not talking about billions of bacteria, kilograms of bacteria, but a few bacteria, come from Earth. Of course, they're going to eat it. They're going to destroy the bacteria because they already have the happy family of Martian colony of bacteria. The same way, if those bacteria from Mars will be brought to Earth, and again in a small amount, we need to take special care not to expose them to the Earth bacteria, because I'm pretty sure that they're going to kill them too. So that's the answer to this question. So that basically we need to understand this kind of a biochemical equilibrium of bacterial colonies. Mm-hmm. By the way, talking about that, when you go to Atacama Desert, this is the driest place, the harshest place on Earth. When the place where you with the fewest possible bacteria on the planet, it's in Chile. Okay, so the Atacama place, Atacama Desert, is a desert with the precipitation frequency like one rain every few hundred years. At that. So if you don't have water, the humidity is only 23%. So bacteria work together, and so you see the bacterial mats. They cannot live, by themselves. They live in a colony, and there is a small minimum size of the colony they can survive because they help each other. So the collaborative effort is very important, even at the bacterial level.
As we were speaking about the Mars, I would like to ask you another question about that. There was this assumption that life on Earth was sent from the Mars, like there was a planet, there was a life there, and then they have sent the examples to the Earth, and then everything was destroyed there. So what do you think about that?
Okay, so this idea that life started on Mars first and then was brought to Earth, was put forward by one of my collaborators, Stephen Benner, who basically just found that in order to proceed with the complex molecules of life, you need boron. And Mars has a lot of boron. They say, oh, they have a lot of boron. If you don't have boron, then the whole process of complexization starts, will stop, creating some kind of, complex molecules, but like asphalt, as you can have a lot of molecules, but has nothing to do with life, very complex, because, so you need certain bonds to be formed. And the boron was very instrumental, and that's how that was the only, justification for him to say that it started from Mars. Well, again, as the Duke, the one known chemist and biologist, says that life is probably obligatory state of matter in the universe. It happens everywhere where the conditions are available. It may start on Earth, on Mars, on Venus, on any kind of exoplanets. So if you have enough energy, if you have enough, molecules in order to start with the source molecules and water, basically. So that's why I think that life is much more universal than only Martian life. Well, it's possible.
It's possible. Okay, thank you. And there is a question from Diana and Anna, but Milena wants to have like a summary of the idea, and she wrote, on the other hand, how can we be sure that rover wouldn't carry these bacteria from Earth?
Yeah, given that, as I said, we have a planetary protection program at NASA headquarters, which is only about 20 minutes away from my house. We spend millions of dollars taking precautions, sterilizing all the space equipment and rovers, working in extremely sterile conditions in clean rooms. Okay, so the clean rooms meaning that like 10 to the minus 5, 10 to the minus 6. So in this kind of clean rooms, I'm talking about the amount of dust and the amount of other particles that can be, and then sterilizing using the UV emission, extreme UV emission that kills any kind of possible life forms. Okay, so from that point of view, I'm pretty sure that we did, you know, a good job. Because this problem was, people were aware about the contamination for many years, at least 15 years, 20 years. So that's why I'm pretty sure that you know, NASA was very serious about it, and I would imagine that no contamination will happen if we find something there that will be of Martian origin.
Okay, so they are thinking about. Okay,
Yeah.
thank you. So feel free to ask questions, and then after we will read in the social media the questions. So Diana, the floor is yours.
Oh, can you hear me?
Yes, yeah.
Yes.
Yeah, thank you very much, dear professor. That was very, very awesome presentation. Well, the highest expectations, so filled with humor. So I have this several questions for you. I am also a nuclear scientist, future nuclear scientist, and I'm studying a little smart kids. So one time my school kid asked me a question. Can you tell me how life on Earth starts? I say, how? He said, comet comes to our Earth long time ago and life starts. He is 8 years old. Can you imagine 8 years old? And every time I was wondering about this question, is he right or wrong? So it is possible that some comet brings life to our Earth.
From Mars.
Yeah. Excellent
somewhere
question.
else. Yeah.
Excellent question, Anna. Thanks for asking. Yes, so comets are just recently we learned that you know, comets are excellent sources of biological material. Well, at least organic molecules that are important for life. So there is one comet, it's called the 61P, you know, the Churyumov-Gerasimenko comet were discovered by two Russian scientists, Churyumov and Gerasimenko. That's why it's called Churyumov-Gerasimenko comet. And this comet was observed, you know, by Rosetta mission. It's a European mission when the, you know, the spacecraft was basically entering the coma of the comet, the head of the comet, and that it has some kind of a, you know, this material that could capture these molecules and dust from the comet and then brought back to Earth. And then we looked at it and we found that, you know, and from that mission and from other, you know, observations from Hubble Space Telescope, that many comets have amino acids. I have those, you know, the building blocks of protein. So yeah, we didn't realize that before, but over the last few years, we become more and more aware that it's not that hard to create biological, pre-biological molecules, I would say, you know, anywhere where it's possible, where there is an energy. Because comets have, it's like a dirty ice. It has a lot of carbon, nitrogen, you know, water vapor in frozen way. And once it's irradiated by those particles that I was talking about, not necessarily the Earth, you can start catalyzing these molecules, creating more complex. And once the comet hits the Earth, yeah, it can deliver biological molecules, of course. So it was actually suggested by Carl Sagan, back to 70s. I mean, in Nature. So this is the matter of scientific papers to show that, yeah, I mean, if you can create those molecules so that you can deliver them to Earth. But the question is that scientists still don't understand, is that how much do you need? Because you need certain saturated amount of molecules in order to start to catalyze and to create the DNA. And so, but then, you know, when you have this big a comet hitting the Earth at that site of impact, it creates very high temperatures, and these high temperatures can destroy those molecules. I mean, you know, the more complex the molecule is, more, you know, gentle it is, the more volatile it is, the easier to destroy. So the simple molecule is harder to destroy, like N2, like molecule of the nitrogen molecule, but those complex molecules, amino acids, easier to destroy, or might be even not even at the level of pre-DNA or RNA molecules. So therefore, my again, I say that, you know, as a scientist who doesn't know everything, knows something, I would say that my opinion is that this idea about the comets as a sources of life is appealing, very interesting, because again, can bring a lot of you know, biological material to Earth. But again, the question is how much it can bring it, because you need frequent collisions, especially early on. And the second, whether those molecules can survive. So this is two unknowns.
Yeah, thank you very much. I wanted to continue this question. Why I asked, because this year I was in Dubna, Russia, and there was a presentation about comets, life on the Earth, the origin of the life on the Earth. So they showed us unpublished but very proving pictures of comets. They zoomed them by electron microscope. So we saw some kind of very basic structures of carbon, oxygen, life beings. So that's why I particularly asked that question. There are so many opinions about that. Maybe there was some part of the comet that, well, it separates from the Earth, rotates some kind of time and returns back to the Earth. Maybe it comes from the other planet. So that's why I asked this question.
Yeah. So what I'm just trying to say that, you know, our planet, because of the volcanic activity and tectonic activity, created those, you know, prerequisite gases, prerequisite molecules that can be used in order to catalyze it. So it doesn't mean that other sources cannot bring it over, but the question is that, you know, it's like Occam's razor, right? So this guy, the you know, ancient priest, and I would say that also a scientist, Occam, came up with the idea that do not multiply ideas unnecessarily. Start with the simplest ideas, and if they don't work, add more and more elements and more assumptions. What I'm saying is that if we can start with our planet, and if we can create conditions and explain the life, you know, within our planet without bringing anything else, if we say that, or if we cannot, then let's bring comets, let's bring meteorites, let's bring, you know, some extraterrestrial organisms or whatever, so or aliens. So yeah, we can bring whatever we want, but I'm saying that we should always start with the simplest assumption and proceed with this. But yeah, again, comets are very exciting sources of biology.
So thank you, Anna. And so there is a question from Diana. Diana, can you join the?
You can ask in Armenian too. Armenian, Russian, or English.
So first of all, thank you for this amazing lecture and the information that you provided us. I have two main questions. The first one is, it's certainly obvious that nowadays scientists, if not all, then most scientists, goal is to find out second planet, so which will be habitable for people. And my question is, what other missions scientists have besides this specific topic? And the next one is, Can data scientists pursue his career or her career in astrophysics and in astronomy? Thank you.
Thanks for a great question. Yeah, let me start with the data science, data mining. So this is the golden age for data science, in astrophysics and in heliophysics. Now that we have so much data, we have billions of data sets, and we're trying to recognize some patterns. So, for instance, as I showed you, this images of Kepler Space Telescope, or the James Webb, that will be even much more powerful. We will see different signals, and these different signals can have different nature, can have the different nature from the star or nature from the planet, and we want to disentangle one from another. So therefore, we want to look for some kind of a pattern. So therefore, if we use artificial intelligence, and if we can tune the system in with our assumption, and if we know what we're looking for, we can look for those patterns. This is exactly what NASA is doing now, is basically using the power of neural networks and artificial intelligence to train the system, the networks, in order to recognize certain patterns. For instance, we're trying to forecast and predict flares from the sun, when the next flare will start. And there's many factors, and we don't have a good theory that can take all the factors into account, but we know that certain factors that contribute to it. So therefore, we know how to tune in the system in the best way to get something interesting. So therefore, with those new missions coming in, like James Webb Space Telescope, and that will be launched actually next year, next November, and then Mars 2020, this Perseverance rover that will get a lot of information about Martian atmosphere, and from these mega surveys, cosmological surveys, and surveys of many stars that we observe. We want to also find out the patterns of the large scale of our universe. It's a cosmological question. So yeah, as far as I know, this data mining would become one essential driving force of science, because we have so a few, I would say, well-developed theories, and so therefore we are more and more looking at some kind of patterns first, in order to understand what drives those patterns. Did I answer your question?
I think so. Diana, are you there? Yes.
Yes, for your answers.
You're welcome.
Thank you too. Thank you for activity. So there is another question from social media. The question is from Vatiter Beglarian, and she's asking, what are the key area of research of solar research today? And I want to add that I know that now solar physics is not that in high priority, because the solar is not active now as it was in after 10 years ago. So it is interesting to hear from you. What do you think?
This is a wonderful question, but I would say that I don't think that the sun is not high priority because it's now not very active. It is, that is correct. It's close to solar. It's in the solar minimum and looks like quiet. But if you look at the statistics of those big events, big flares, that the number of flares normally increase dramatically during solar maximum. That comes and goes every 5.5 years. So, and now the frequency to expect a flare, the frequency of occurrence of a flare is pretty low. But because sun has more opportunities to accumulate large amount of energy. It's like a spring, you know. You add more amount of magnetic energy, you add more stress. And the statistics shows that during those quiet times, we had those biggest flares that can create havoc, problems for our civilization. So that's why we're looking for those quiet times create extraordinary opportunities for us to study formation of star spots, and if those star spots can grow bigger and bigger and bigger and bigger because there is no other factors, and then accumulate the energy and then release this energy. So yeah, I think that you know, despite of this quiet period of the solar activity, solar physics has a lot of problems to solve, because some of them are also, it's so-called nano flares, extremely small flares that makes our corona hot. If you don't have the big flares, you remove those distracting factors of the big flares, you concentrate on the background. You want to first understand the background, right? And now it's a unique opportunity to do so.
Actually, yes, and you were speaking about the climate change, and you are saying that global changing is going to be warm now, but there is assumption that when sunspots number is going down, we will have not like warming, but we will have climate cooling.
Yeah. Cooling. Yeah, well, yes, so maybe. Again, so this question is under debate. So, and I don't want to speculate. It may be the case. For instance, we had this case with the, you know, back to Maunder minimum, back to 1670, 1650, 1655, for like, you know, 70 years. The so-called Maunder minimum, when the sun was under the extremely deep minimum, super quiet. And by some reason, which we still don't understand, because we don't have a good theoretical model for it, but we know that coincided with the period when the Thames, you know, the river, Thames River in England was completely frozen. And we have pictures when people were ice skating on Thames River. That only happened that time. So, and we know that Europe was unusually cold over that time period. Now, is that a coincidence, or it's the, you know, has a causal relationship? We don't know. Maybe.
So we will see. We hope so. So there is a question from Susanna Gevorkian. We can ask her to turn on microphone and ask question.
Oh yeah, which is the most interesting signal from space that you received, observed? Okay, interesting question. Never received this kind of question. What's the most interesting signal from space that I receive and observe?
You need to think and prepare.
Well, I probably can say so. Yeah. So the most interesting signal that not I received, because I'm not an observer, but that you know, I used to interpret, for interpretation, is the as I said, the most interesting and unusual and crazy, and we're receiving every single day from Kepler, now from TESS. It's the signals of exoplanetary, you know, of exoplanets. So now we learn that exoplanets come in different sizes, they come in different masses, and so we see exoplanets that we've never seen in our solar system. Because look, in our solar system, we see like Earth-like planets and a little bit smaller. Mars is smaller. Venus is like Earth, it's like Earth's sister. Okay, Mercury is smaller. So we have so-called terrestrial type planets, and then we have the big planets. Okay, we have Jupiter, which is about 11 times bigger in size and about 300 times in mass. Okay, so we have very massive planets, and we have like Earth mass planets. Okay, between like 1 and 300 in mass. So now, and nothing else. And we thought it's a normal thing. So the one interesting signal that we see from Kepler is that, wow, we have a so-called super Earth. We see some planets that about as 10 times bigger in mass, more massive than our planet, but size about 2 times bigger in size. And they are, by the way, the most populous. You know, so many of them we observe around other stars, and we don't even have a single planet in our solar system. So it looks like that the one interesting thing that I observed, that our solar system looks like is unique by itself, and other solar systems are very, very, you know, very, very diverse.
Thank you very much, Professor. It was very interesting. And I have one more question about nanoparticles in space. Or what damage can cause nanoparticles? I know that they can damage spacecraft.
Well, yes, they may damage a spacecraft. They can create some overcharge it. Yeah, so this is the question of the planetary protection. So now that we have so much garbage in space, so yeah, and it's not only the cosmic dust I think you're talking about. Yeah, we're talking about those particles from the larger size all the to the nanoscale that you know, can collide with the spacecraft, given that the spacecraft, you know, orbits the Earth at you know, few tens of kilometers per second, so like you know, 8 to 10 kilometers per second. So and at that point, or with some kind of an interplanetary spacecraft that can go in faster. So if you add the velocities of two particles, then the speed can be pretty dramatic, up to 40 kilometers per second. So that kinetic energy can be really high to destroy it. Yeah, it's always a I would say a danger. Yeah, and sometimes it can kill the electronics. By the way, talking about that's nanoparticles, is not exactly a nanoparticle, but you know, every time we have a big flare from the sun, those particles forming, you know, those energetic protons that come from the sun can kill electronics, and we did see that happens. And also, you know, this the electric currents excited by the perturbation of the magnetosphere, magnetic field, can also induce electric currents that can damage electronics at Earth, on Earth. So yeah, it is a problem, so yeah, so far as I understand that, you know, we have to be lucky, you know, to avoid it. Take some precautions, but you cannot take all the precautions.
Thank you very much. And I'm sorry, but I have one more question.
Right.
Feel free.
I think there should be some research groups on nanoparticles from space. They exist or no?
Yes, they do, but I cannot refer to any research group immediately. So if you send me an email, I can find the group and connect you to a specific group who deals with nanoparticles.
Thank you very much.
I'm not ready to answer this question immediately, because I know that they exist, but I don't know where. But
I guess Susanna is doing some research connected with the nanoparticles, and that would be extremely helpful for her to be connected with the group.
Sure, of course. Yeah. If she sends me an email at vladimir.Hayrapetyani@nasa.gov.
I will share your contact with the interested parties, so that would be not a problem. So if there is any,
you're welcome,
Susanna, if there is any other question here, so that there is one more question from Diana. Is there a chance to save the planet from global warming, weather, or not? You detect new habitable planets, so there is actually two questions. So can we save from the global warming?
Okay. So the first question is that can we be saved from global warming? Is that the question? Well, the global warming, yes, it is a reality, of course, and despite of the the political, a lot of political opinions about it, but the scientific opinion that it is a reality, and carbon dioxide level increases drastically over the last, and now it exceeds 400 parts per million, first time in the history. So when it started about 150 years ago. So the one thing that I want to mention is that the natural cycles require tens of thousands of years for the carbon dioxide to vary. And it does vary, of course. It did vary, on Earth at pretty big, very big amplitudes, going back and forth. But it takes tens of thousands to hundreds of thousands of years. It's the first time in history that cannot be explained other than the anthropogenic, reasons, man-made. That in just 100 years, in 1 century, you have such a huge increase in carbon dioxide. So, so now, if we don't do anything, of course, it will keep increasing. But if we do something now, the oceans are now so heated, so warmed, that because of the huge, thermal conduction, the capacity of the thermal capacity of ocean. So that ocean is harder to heat and then harder to warm. It will take another 50 years, to cool down the ocean. So the ocean will contribute to the global warming if we don't even do anything now. We already did the damage. So, and I don't know, this question is still under debate, whether, how much the future generations, like your generation, will feel. And I would imagine that the frequency and the strength of hurricanes will increase, of course. So unfortunately, the ocean will contribute to the overall global warming.
Actually, yes, but there is another aspect as well, but it's a huge topic to discuss. As I say, that there is assumption also for the global cooling. And so actually, thank you for a question, but it can be another topic for the discussion.
Right.
Thank you for the...
and the question was that how to detect new habitable planets.
Yes.
So, okay. So, I wanted to briefly mention it because I didn't talk about it. So the point is that when, if you remember one of my first slides, was this a plot, right? Those dots, if you remember, 4,000 dots, the size of the planet versus the rotation period of the planet, and I showed that some of them are Earth-like planets. Depending on the mass and the spectral class of a star, if the star is brighter and hotter, so then, the planet should be farther away in order to receive enough heat to heat the planet to between 0 to 100 degrees Celsius, to have water in liquid phase. It's called the habitable zone. Okay, so the habitable zone is the first condition. It's not doesn't mean the life there, but it's the first condition that is required, absolutely required, for life to be started and developed and function. So now we have already few tens of cases of exoplanets like Earth size I'm talking about in the habitable zone, which gives us a pretty good hope that other factors can also be in place. For instance, I was a co-author on one of the papers that was recently published in Astrophysical Journal and was advertised, with, with a lot of media and CNN and other sources. It's a TOI 700D. It's the target of opportunity, the target of interest, sorry, observed by TESS, by the Transiting Exoplanet Survey satellite. So it's interesting system when the star is very inactive, doesn't show a lot of flares. So it cannot deteriorate the planet and evaporate the atmosphere. And the star was at about 0.16 astronomical unit away, which about, a little bit closer than Mercury, but because the star by itself is much smaller and dimmer, at that distance of 0.16, it's about 6 times closer than we are from the sun. Okay, but because it's not actual sun, but cooler than sun and dimmer than sun, it receives less energy. So the planet should be 6 times closer to the star in order to receive exactly the amount of energy that we receive from the sun, to have a temperature between 0 and 100 degrees Celsius. Okay, so yeah, so we have those few cases that will be observed for future missions, including James Webb Space Telescope. So I am hopeful that we will detect with James Webb at least some crude, I'm not saying one life, but some crude spectral signatures of atmospheres that will tell us that we're on the right path, but we're moving in the right direction towards the finding life.
Okay, thank you for answer and thank you for your time today.
So
that we will continue. Sorry, Diana. Sorry. Hope we will continue to have presentations and meetings with you. Thank you for all participants, and see you soon.